Hello, everyone. My name's Louis, and I got a 49 out of 50 in the chemistry external exam in 2024. And um, I'm here to talk about today the reaction pathways in chemistry for the QCAA external exams. Part of the syllabus is learning these pathways. So, as you can see here in this image, this is the one directly from the QCAA syllabus on the dot points of the general overview of what you need to know, in surface level. And then I have some tips here for you, and then I'll go through talking about what they are. And then I have an extra one as well, diagram, which has more detail about what are the reagents that help with um, undergoing the reactions and some of the, drawn out um, carbon structures and things like that to help, with understanding why for example, an alcohol from primary alcohol goes to an aldehyde through oxidation and how that happens, So, um, there are obviously lots of resources to learn about reaction pathways, but I've done this video because someone has requested it for me to do it. So, it's definitely something that is quite high yield and that you need to know. Some of it's rote learning, but you can actually sort of understand what the processes that are happening here in order to answer some questions. And once I've done explaining this background knowledge, then I'll walk you through two short answer-based questions from past papers that involve, the reaction pathways and showing you how we can solve them bit by bit. And with the questions, you'll seem to understand that they really ask about broader, more high yield things rather than, that particularly, not just mindlessly memorizing this diagram, but you also need to understand it. Okay. So I'll start off with some tips that I have for you. Bookit is a really good website that basically there are pre-made flashcards or like questions or sets, that you can do. If you just search up QCAA chemistry pathways or QC pathways, chemistry pathways and that sort of thing, then you'll find a lot of online public sets, but you can also obviously make your own. And you can even upload, maybe you had your lesson slides from class, and then you can upload as well if you prefer that way, and then it will AI generate those flashcards. But basically, it's like a game type thing to make it sort of fun. But you can choose different game modes, and whenever you get a question right, you increase in points, and then you can sort of like either build something or complete the task as well. Like I know there's the one I use is Tower Defense. That's one of the games I played in Bookit. And basically, you have multiple choice questions for the reaction pathways if you choose that deck to study. And then, for example, it might ask you, like, what are the reagents that for substitution from a haloalkane to dihaloalkane? Okay, and then one of the options which is correct is the X2 and UV light. And so if you click that one, then you progress well, and you progress through the game, right? And another one you can use is Anki as well. There may be pre-made flashcards. I'm pretty sure there will be pre-made flashcards on like QCAA or QC chemistry reaction pathways. So those are the types of words to put into your search bar is, QCAA, QCE, chemistry, year 12, and those sort of things will help you find what you need to find. Or just any app or website that makes flashcards or has those pre-made flashcards to save you time. I do understand that you have your chemistry exam coming up in 2 weeks. So on the 7th of November now. And so that honestly, I know it can be stressful looking at this, but it's actually not that bad compared to what we have to learn medicine and everything. This is really just a starter, and so it's really good to just try and wrap your head around this as best you can. But 2 weeks is plenty of time to learn the pathways, so I wouldn't stress too much at this point. Okay, another tip that I can give you that's high yield is to make sure you draw out the pathways. Okay, especially in courses, in university courses where you have pathways just like these, it's so crucial to make sure you draw them out and actually write them with either if you have an iPad or just on a piece of paper, right, in your book, because drawing them out will help you to retain and memorize that information better rather than just copying pasting images or doing other things as well. Okay, now another tip I can give you is making sure or a suggestion is to watch this guy. Here, that's his YouTube channel name, Daniel's QCE, and he literally basically saved my life for the chemistry externals in terms of reaction pathways. I mean, a couple of weeks prior to the chemistry externals in 2024, we had ours much earlier. Earlier than yours. I think we had it in the first week. I think second week, but the Monday of exam period. And so I really felt cooked with the reaction pathways, but it got so much better when I watched this video, and he has even a Google Drive in the description link regarding giving out basically a free chemistry flowchart reaction pathways that's really detailed, probably even much more detailed than this, than you really need to know. But I guess to score those really high marks, you need to, learn as many details as possible, because they can really assess you, mainly on those dot points, but also making sure that you also know, the high yield details at least between each step. Okay, so I might just walk through the reaction pathways. So the easiest I find to learn first is oxidation, okay, because it's pretty much just from an alcohol origin. We have our primary and secondary alcohol types, okay, and make sure, again, you really draw out those pathways. So when I mean draw out, I mean literally just draw out the chemical structure for a primary alcohol and a secondary alcohol, and then do that for everything else as well. Okay, so primary alcohol, we oxidize it, that becomes an aldehyde. Okay, and then we oxidize that again, and we have a carboxylic acid. Okay, so the way I remember it is just use the acronym of the first letters, PAC, and then SK, is just the secondary alcohol to the ketone. Okay, so PAC-SK or something like that. Okay, and really what oxidation is really doing is that from the alcohol to either aldehyde or ketone, we have mild heat, we have dichromate, I believe that's dichromate, yep, and MnO4 minus in strong acid. Okay, and what that really does, I believe, is creating that double bond on the oxygen. So remember, from an alcohol, we have the chemical sort of composition here. We have an R group, but then the OH is really what makes it an alcohol, which is a single bond. But aldehydes and ketones, they have that double bond, okay? And by oxidizing, we basically add an extra bond from the C to O to make that a carbonyl group there. Okay, so these are our carbonyl groups. Okay, so once you've done oxidation down pat, then I would literally go in this order. So oxidation and reduction. Okay, so with reduction, there are also like sort of two pathways as well. So we can get an alkene to an alkane and a nitrile to an amine. Okay, and basically with reduction, I believe it's just plugging in a H2 and the, I guess, reagent or substrate is like a nickel to help with reduction. There, so those are also easy ones to do. How I remember reduction is it's just basically reducing those double bonds. Okay, so excuse me. For example, an alkene has a double bond on these two carbons, but then on an alkane we have only one bond, single bond. And so that's how I remember a reduction. And basically what happens is, obviously if you plug in H2 into an alkene, then you'll be breaking that bond and then having more H's around the carbons, right? So for example, you'd only really have 2 hydrogens on each carbon, right? Because remember, a carbon with the octet rule, we have 4 valence electrons around a carbon, and that means we have 4 possible pairs to combine it with. With an alkene on this carbon, we have 1, 2, 3, 4 lines or 4 bonds, right? But on an alkane, we only have 1 bond here between them, so that means there's going to be 3 hydrogens on each carbon. Okay, and that kind of makes sense why we're adding 2 hydrogens, is because we need those hydrogens to be bonded to the carbon instead of that double bond with the carbons together, right? And then with the nitriles, again, it's quite self-explanatory. If you add a H2 to the nitrile, then we actually reduce those double bonds to just one, where we just have the NH2, and that's a single bond to the R group. And by R group, we basically just mean like any sort of carbon chain, or can be other additional parts to it. But really, the reason why we talk about an R group is because when we're defining, or I guess categorizing amines or nitriles or all these different chemical compositions, what really matters is the N part of the R group, such as the OH is alcohol. That's how I remember it, is that OH is literally in the word alcohol. Same with nitrile. This R, if we have a C triple bond to N, then that immediately tells us it's a nitrile. Okay, we don't care about necessarily what's in the R group, but once we see a C triple bond to N, we know we can classify that as a nitrile. Okay, all right. And then once we've done reduction, I would personally I would go to condensation next. And the reason for that, sorry, I said I would do in order, but now I'm thinking about it. And the reason for that is because we've just done oxidation and, well, yeah, we've done reduction. But with condensation, that's using basically the same elements we've used from oxidation, our first thing we learned, and combining the reactant and the product, end product, if you think of it like that, with combining those two to form a new product, right? So the 2 condensation reactions we really need to know are just alcohol, can't spell, alcohol plus carboxylic acid becomes an ester, and there's a hidden H2O as well. And my challenge for you is to figure out why that might be the case. Draw out an alcohol and then draw out a carboxylic acid. And then if you combine those two, try and figure out why we have an ester plus H2O left over. So in other words, I'm trying to take out a H2O somehow, and I'm forming an ester, which is just a double bond to O and single bond to O on the carbon, but then there's another R group. So it's basically a carboxylic acid, but in the middle, basically. Okay. So that's something you can have a look at, and definitely watch Daniel's QC's videos and all that as well. And then the other one is an amine plus carboxylic acid becomes amide. Okay, and an amide basically, remember usually with ides and stuff, there's usually a double bond to O. And so it's basically you can call it an amine group, but with a carbonyl or C double bond to O just preceding or before the NH2. There. So we've done condensation reactions. I reckon the best place to go next would be addition, simply because addition really only originates apparently from alkenes, which, yeah, that works out here as well. Yeah, okay. And note the different catalysts as well for the 4 different addition reactions. And it sort of makes sense if you really look and understand this diagram. For example, an alkene to a dihaloalkane, well, we would have our halogen group like an X. So say it was in this case Br was bromine. If we have 2 of bromines and we add that to an alkene, well, we're breaking that bond, basically stuffing it in there. That's how I remember it, as addition is equal to just stuffing it in. Okay, so I'm stuffing my X2 or X we're talking about halogens such as bromine, chlorine, what else? Fluorine, and there was one other one. I forgot now, but yeah. We can understand why addition from an alkene to dihaloalkane would have the, I guess, reagent or what we need to create this reaction for addition is the 2 halogens, right? Because we need to form the product. Okay. So those are the 4 reactions. So that was one of them, alkene to dihaloalkane. But we can also just do alkene to haloalkane. You can imagine that's just basically one of the halogens, but remember that has to be, because halogens are usually, they have 7 valence electrons, so they have 1 possible bond they can make, so there needs to be a hydrogen as well with that. And it matches out, because if we break this double bond, we have 2 sort of bonds we need to account for now, because we need an extra bond on one of the carbons and an extra bond on one of the carbons, right? So that's why we need a hydrogen on one and then a halogen on one, okay? And so that's where we get our R and X, okay? So for example, in this case, I think that's a ethene. If we do our addition reaction from alkene to haloalkane, and let's say we add a HBr, bromine, hydrogen bromine, then what we get will be just those 2 carbons. Okay, we haven't changed anything with the carbons. We haven't changed anything with the current hydrogen bonds, but because we broke that double bond, we need an extra bonds for these carbons. So those question marks are sort of pondering like, well, what do we add for that reaction? We added a hydrogen and we added our X, which in this case would be bromine. Okay, and so that would be our haloalkane. Okay. Yeah. And then another addition reaction we would know is alkane to polyalkane. Okay. So remember, I think you've done your I3s, and most of you probably would have had an option to do polymers. And with polyalkanes, they're basically their bonds are, I believe they're heated, but don't quote me on that. Yes, well, I guess catalyst, heat, and pressure. That's the catalyst for addition reactions from alkene to polyalkene. Is it polyalkene or sorry? That should be say polyalkane, and it makes sense because there's no double bonds. But yeah, I guess if you add lots of heat and pressure with the alkene, I guess it breaks those bonds because of the boiling point and melting point, I guess, and that forms polyalkene, alkane, and that sort of continues on with the N here. That's basically signifies that the N basically tells us the number of alkanes in our polyalkane, because poly means many, so many alkanes. Okay, and then our final addition reaction, which would obviously lead to our other stuff we learned before. I'll talk about hydrolysis in a sec, and is an addition reaction from an alkene to an alcohol. And the reagents would be water. So we add water to form an alcohol. Kind of makes sense because you need that OH. And then you need strong acid and a heat and pressure as well. It's sort of similar to the polyalkane there. Okay. So we've done addition. Now let's look at elimination. And for those of you wondering, I will, every video that I post has a link in the description to this OneNote, this entire OneNote right here for Louis Gowan QCAA tutoring. And so you're happy to go through this as well if you'd like. Now, what else? Or what are we up to? So elimination. Okay, so there's really one elimination reaction we need to worry about, and that's just the haloalkane to the alkene. So we can basically transverse that addition reaction if we add sodium hydroxide, NaOH, and heat, then we can actually form that haloalkane back into an alkene. I don't know too much about how that happens, but definitely watch Daniel's QC video on that. I think he explains pretty much the reasons behind all these reactions pretty well, or other videos and stuff like that. But I'm truly sorry, I don't know too much about the NaOH and heat, how that forms the elimination reaction. But just knowing that's, I guess, the most important part. And then with substitution, there's quite a few substitutions actually. There's an extra one that this diagram gives with an haloalkane to an alcohol, and that's a substitution, but it's similar to the elimination reaction. So I'm not too sure if that needs to be considered, but I might just quickly draw that as well. Okay. Yeah, so give or take, there's probably like 4 or 5 substitution reactions that you need to know. I would personally learn 5 just in case they sneak one in, but I think going by the QCAA, you still be safe because this is what they gave anyway. But it's better to be safe than sorry. But basically, with substitution reactions, most of it is really just adding, um, I guess, adding something extra to it. So substituting, for example, and then obviously, I believe you would, um, you'd form different compounds in there. So, for example, alkane to haloalkene, you can sort of understand why it's substitution because I guess we're adding that X group to form that halogen within our alkane. Same thing if we do it for a dihaloalkane. We need an extra halogen. And so we're substituting that halogen in as well there. Um, the other substitutions, so most of these actually come from a haloalkane, which is quite interesting. Um, so from the top of the diagram, we have the haloalkane not just going to make more halogens, but we can actually remove those halogens and make something else on this side with the amines and the NH sort of things. So we can actually convert a haloalkane to a nitrile using KCN. And the way I remember that, and heat as well as the factor. And the way I remember the KCN is because it's literally this form. Because remember carbon, so let's say our K, well, we know K, which is potassium. It has a positive charge, so it can get an additional bond. So K to carbon, and then it's literally 3 bonds to nitrogen. Because we know nitrogen has 5 valence electrons. So to make the octet, which is 8, we need 3 bonds. So that makes out there. Okay. And so obviously to get a nitrile with a C triple bond to N, we would need that factor, the KCN. I forgot what that was called, but it's just KCN. Substitution for haloalkane to amine. Well, we don't need that triple bond. We're only making a single bond, so it's quite easy to remember NH3. Okay, just note the NH3 as opposed to NH2. We're not just adding an amine group. We need to add an ammonia group, NH3, I believe, is ammonia, and heat in order to, I guess, fill in the extra bonds that are needed when we break that carbon group or that R group to fill in for the haloalkane that's missing. And I believe as well you have another product from a substitution reaction, like the extras that were substituted out, I guess. But Daniel's QC videos talk about that pretty well as well. Okay. All right, so now on to the past paper questions. So this is 2022 paper 2, and it was the first question that came up for 8 marks in total. And obviously we have our A, B's, and C's and stuff. So the diagram shows a series of different reactions starting with compound A, which has the empirical formula C4H10O. Okay. Identify the class of organic compounds that compound A belongs to. Now there's a couple of ways to solve this question. One might be through, you may not even need to use the pathways if you understand how to draw out C4H10O. So basically, remember, just start with your carbon chain. So just start simple with just 4 single bond carbons, and then add your H's in. So this would be butane, but obviously there's an O, and we need to add that in. So what I usually do is I go from the basic structure, an alkane, and I think about, okay, do I have enough carbons? Do I have enough hydrogens? Do I need to remove some hydrogens particular, or add some hydrogens? to this to get my actual class of the chemical compound, right? So organic compound. So I count my hydrogens. I have 4 on the top, 4 on the bottom. So 4 plus 4 is 8, plus 2 is 10. Okay. And then from that, I sort of see, okay, there's 10 hydrogens in my alkane model, our template. I have 10 hydrogens in my empirical formula, and my O, I don't have any O's at the moment. So that means I can just plug in O here without affecting any of the hydrogens. I still have 10 hydrogens, and that will be my actual, I guess, organic compound written out fully for this empirical formula. And we know, for example, what we learned above with the reaction pathways. Again, this is like high yield knowledge. It's not necessarily a reaction pathway question, but it relates to it. We have an R group, which is all our carbon chain, single bond to an OH group, which is a, I want to say, I forgot what that was called, but anyway, with OH, we know that the class of the compound is an alcohol. So all you got to say is just alcohol. Okay? So that will give you the mark. Okay? Identify the class as alcohol. Right? Now for 4 marks, so this is quite a high yield one. Okay? We have part B, but it's split into part I and part II. So compound C is an isomer of compound A, right? Oh, and sorry, I might talk about how you can, there's another way you can solve this, part A question 1A, using pathways. So if we have butanoic acid, which is, we know that as a carboxylic acid, because that's the nomenclature or naming system of that. If we have these reactants, dichromate and H plus or strong acid, then think about when we had a look and learned about these pathways, what I guess type of reactions would have those reagents? It would be oxidation, right? And we learned from the very start that oxidation is from an alcohol to a can either be to a primary alcohol or a secondary alcohol, and then from a primary alcohol, if it was a primary alcohol, it would become a carboxylic acid, which is this step here, which is E, right? And so it makes sense that this would have been a primary that would be a aldehyde, D would be an aldehyde, and then A would be a primary alcohol. Because we basically have 2 oxidation steps, which basically mimics this entire step right here in the pathway in yellow. Okay? So that's a way to also remember it. Okay? So that's really a telltale sign. If you see these 3 different compounds being made, it's most likely, and obviously the reagents are dichromate, is most likely a primary alcohol from the beginning, becoming an aldehyde, and then a carboxylic acid in the end. Okay, so sorry about that. But yeah, part B, compound C is an isomer of compound A, deduced structural formulas, and IUPAC names of compounds A and C. Okay, so we know that compound A is, well, we basically drew it out actually, so that's a good thing about using the first method of, figuring out part A, is because we literally do 2 steps ahead and we actually found the compound A structural formula. And so when it's asked about the structural formula, that's really about drawing out the full, I would personally draw out the full um, I guess, chain with all the carbons and hydrogen bonds, I wouldn't do skeleton structure unless it specifically asked me to do a skeleton structure formula, just because I would put as many detail as I can, as long as it's accurate, because that will save me from losing marks, and it'll because you can't lose marks from putting too much information, um, especially in a question like this where it's quite vague and it doesn't tell you what type of structure formula to use. And so that's why I would definitely go with, I might, just to save time, I might just copy this over here. And then I would even like separate this oxygen bond to a hydrogen there, just to be really sure that I'm showing that everything is single bonded, okay? And that I have all my components, right? And so, yeah, that's the mark there. If you draw out that butanol, which is our IUPAC name, so remember when we break down the name, an means an alkane, basically, and ol is our alcohol group. Because alkane means single bonds, and alcohol is obviously that OH group, okay, at the end of the carbon, single bonds. And but basically mean 4 carbons, or like 4 as well, okay? So I guess message there is to, and that's the mark, message there is to really revise your nomenclature and your naming systems for IUPAC. And yeah, I guess breaking it up into those different parts of the word really helps as well. So yeah, and then we need to find an isomer for compound A. Now with isomers, the easiest thing I can tell you is to, you remember that R group we were talking about? That ROH group? Now this OH group, can be moved around and essentially become an isomer, as long as you keep it all consistent and you have all your compounds, right? So instead of putting my OH on the first carbon, because this would be our first carbon, what if I put it on the second carbon, right? So I'll have to move stuff around and be really careful that I'm doing this properly. So again, I'm going to have my 4 double bonds, and then I'm going to put my OH immediately. I'll just put an OH there. And then thinking about my octet rule for this particular carbon on carbon 2, I need to have an extra hydrogen to make those total 4 bonds. Okay? So there. So I was removing the highlight and then putting my hydrogens in that are extra. And then I want to count and make sure that I've got this right. So 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and then my oxygen is just 1 there, right? So that still fits the formula, which is C4H10O, okay? But it is an isomer. And the IUPAC name, very simply, wherever the oxygen, the OH group is on the carbon, so we number our carbons for, so say this was 1, this is 2, 3, 4. The reason we don't go the other way is because we always want the lowest number possible for our IUPAC naming, okay? So if we go this way, 1, 2, 3, and say that's 3 butanol, that's incorrect, because we always name, the rule is to always name the carbons in order, so number the carbons in order where we have the lowest number in our IUPAC naming system for our main, I guess, sort of groups there. I might search up what the OH group is, just so I'm being accurate. Hydroxyl group. Okay, so this apparently is a hydroxyl group. Okay, and so that is basically, we talk about the significant importance in, I think there's a diagram if you search up, like, I think chemical, organic chemistry, compound naming, or IUPAC, and then there's like a table of like the prioritization of the numbering system. Hydroxyl is pretty high up there, okay, because simply we have an oxygen and hydrogen, so that's sort of quite important in our naming system. So this will obviously now be just the second carbon, and so this is 2-butanol. All right, so 2-butanol. Okay, and so those are our 4 marks there. So quite some easy marks to get, but making sure we're being really comprehensive and accurate there as well, and not taking shortcuts, just to be safe. And identify whether compounds A and C are structural or geometric isomers. These would be structural isomers. Okay, and the reason for that is because with structural isomers, there are really about shifting the structure or the position of things in terms of which carbon they're on. But with geometric isomers, they're talking about which side they are on. So it's still probably going to be the same carbon, but we're talking about cis and trans, as in like trans is the opposite side of relative to another group, and cis is being the same side. And I think there was a question in 2024, my paper, which talks about the geometric isomers. So we'll talk about that then. Okay. And then part D is 2 marks. So again, we got the drawing and the IUPAC name. So and sorry, that was the 1 mark. And then, so with compound F, so if we look back into our diagram, compound F is an ester, okay? And this right here is carboxylic acid, because we have our double OH, which we know, or C double OH, which we know would be just this. Okay, and that's a carboxylic acid at the end. Sorry, OH as well there. Yep. So that's, if I just highlight, that is our carboxylic acid, and that's called a carboxyl group, I believe. C double OH. Okay, and so we know that if we add a primary alcohol with a carboxylic acid, we make an ester. Okay, and we need to sort of think about what happens there, right? So if we have, and this is sort of going back to the pathways, trying to explain why a condensation of alcohol plus carboxylic acid will make an ester. And I did mention I would talk about hydrolysis, but I did forget. But basically, hydrolysis is just going backwards from an ester to an alcohol and carboxylic acid. So just the reverse of a condensation reaction, okay? And in this case, we would obviously add water. So this is basically just this, the condensation reaction here, but backwards. Okay, so ester plus H2O becomes acid plus alcohol. And I believe same thing here. It doesn't show the purple. I might add that there though. So we had an amide that can become a carboxylic acid or a amine. Okay, so we can go back in that way as well. And remember, we'd be making both an acid and carboxylic acid in an amine from amide plus H2O. So again, that's just going backwards. Okay. So if we think about adding these structures, so let's put our primary alcohol first. Be an OH. Okay, and then just next to it, I'm gonna draw the carboxylic acid, and the carboxylic acid we were given is actually it's just 2 carbons, so that would be F, which is 2, and for the single bonds, and oic acid for our carboxylic acid. Okay, so if we draw out ethanoic acid next to it, so we would have 2 carbons and then a carboxyl group as well. And our hydrogens here. Okay. What I might do is I might move my primary alcohol to this side because it's a little bit easier to explain what I'm doing. Okay. So essentially what we're doing when we're doing a condensation reaction, we are removing water. Okay? So think about, if we're removing water, what is water? H2O, right? So 2 hydrogens and 1 oxygen. Now, I want to have a ester, and I remember an ester is just basically a, if I look back in the diagram, ester has only 2 oxygens. I currently have 3 combined with these ones. So I obviously need to take an oxygen out as well, which is part of my water molecule in the end. And if I say that I want to get rid of these 2 H's here on the ends, and then this oxygen here, because I don't want an oxygen just lying around in the end. I don't want a hydroxyl group at the very end of this. I want just basically my group here will just be a C double bond to O, and also single bond to an O, and then an R group after that. So I want that to be in the middle of my thing with nothing else. The R group is just C's and H's. Okay, so you can notice here why I'm taking away specifically this O on the end as opposed to this O, because I want to keep that O for my ester group, because as highlighted in, if I might highlight this in a different color just to be distinct with it. So this is my ester group in green. That is equivalent to this section right here from my my carboxylic acid. So I want to keep that, but I want to remove everything else that might be contributing to those changes. There. Okay. So basically, I'm just removing everything in yellow and keeping everything else the same. Okay? because I have my 2 hydrogens, my oxygen, and I got, and I'll show you once we draw it out again, I've got the ester that I need to have, okay? And so if we draw that out, just basically removing that H2O, we get this right here. Sorry. So remember, I've removed that hydroxyl group in the very end on the right-hand side, making sure that every carbon has 4 bonds. And then I have this group here for the ester. Okay, and so that is our mark there. Okay, so that's just one mark, but we need to put the IUPAC name. And remember, we put in esters, we put the what we originally had for the alcohol first, which is butyl. Okay, because the one that matters the most and that comes in the end is the carboxylic acid group sort of thing, the ester. And so that would be FN, because 2 carbons here, O8, which is our ester naming system. Okay, so butyl ethanoate. All right. All right. So moving on to question 6 of paper 2, 2024 EA. This was 9 marks this time. Okay, so you can see that pathways, they're not going to test you on everything, but they're obviously pretty high yield, giving they can literally give out free marks as well. So question 6, 6 molecules were selected to investigate functional groups and the arrangement of atoms. Part A, identify a molecule that contains a carbonyl functional group. Okay, so in our molecules, we can sort of eliminate or sort of choose which ones we're thinking about. So carbonyl, again, that's the C double bond to O. So we just need to know that. Okay. Carboxyl is the C double bond. C double bond to O and then OH group. And then the other one we learned was hydroxyl, and that's just this double bond to OH. Sorry, single bond to OH. And so the one with the carbonyl group, it's not going to be 4, it's not going to be 5, not 6, okay, not 3. Now it's between 1 and 2. The answer sheet does identify it as molecule 1 or 2, obviously with this, but to be honest, if I want to be more accurate, I would choose molecule 1 because that's much more safer, because molecule 2, you could argue that it's actually a carboxyl with group, given that we also have OH, but it's again up to you. I guess it does contain that carbonyl functional group as well. So molecule 1, identify a geometric isomer of molecule 6 and apply IUPAC rules to name the geometric isomer. Okay, so this is what I was talking about before in the previous question from 2022. Geometric isomers, as opposed to structural isomers, we're not changing necessarily where they are, we're just changing around the position of them in terms of their spatial, I guess, 3D dimensional space. So for example, we have 3 carbons here, right? This chlorine, which I believe this will be a haloalkene, molecule 6. This chlorine is opposite sides to the H3C over here. And we call that a transition. geometric isomer, which is trans 1 chloropropene. Okay, because we have the 3 carbons, so prop, ene is the alkene here. Chlora on the first carbon, this one. And then trans basically tells us that it is on opposite sides. However, note the question's asking us to identify geometric isomer. So basically the other geometric version that we can have for molecule 6. So essentially the opposite of trans is cis in geometric isometry, and it would just be cis 1 chloropropene as our answer there. I'll just copy that. Alright, that's that tick mark there. Okay, now this one basically requires us to know about those reagents again that are both in Daniel's QCE videos and diagram flowchart, as well as this one, I believe. So it's asking us to describe using a balanced chemical equation how molecule 4 can be converted to molecule 5. So this is a nitrile because of the C triple bond to N, and then the molecule 5 is an amine. Okay, so just know those functional groups, and then sorry, not functional groups, organic groups, and just remember our pathways. Nitrile to amine is a reduction reaction, because remember from the diagram just through visual memory that a nitrile is that blue arrow to amine because we're reducing those number of bonds. Okay, and so we need to describe that through a balanced chemical reaction. So we know that we're going to have an extra 4 hydrogens here, and then we're breaking those 2 double bonds there to make it a single bond here, right? So we need to add to our nitrile. So let's just write this formula here and make sure with the balanced chemical equation you have the state of matter. So nitriles would be liquids, okay, and then our 2 hydrogens, 2H2 would be gases, okay, and then that would be converted to that amine. So just drawing it out now, CH3 is this part, CH2 is this part, and then NH2 is the next part. And that would also be a gas. Amines are gas, okay? And then we need to include all relevant reagents. And we remember that the reagents would be nickel as well there. And the marking guide actually gives PT as also a reagent, or as well. So you can write nickel, you can also put PT, which is platinum. Both, I'd say, would give the correct answer. Full marks there. Because one of the marks in this 2-mark question is to determine the balance equation. Okay, we know that it needs to be balanced on both the left and right sides, and that we know we've done that because we have 4 extra hydrogens on the products, then the nitrile, and then we've added those 2H2, so total of 4 hydrogens, sorry. And then the second mark is by identifying an appropriate catalyst. So that can be, I think they'll accept either nickel or platinum as well. So part D now is basically just filling in the blanks for this reaction pathway diagram. So completing the diagram to explain how molecule 3 can be converted into molecule 1 and 2. Okay, so firstly, we look at the reagents or catalysts here, and that's KOH, which is alcoholic, and also heat. Okay, and we need to know what molecule 3 is. Molecule 3 is an haloalkane. Okay, because we have a chlorine here, and we remember our diagrams from a haloalkane, and we have a KOH, which is similar to NaOH, so it's basically another form that we can use for a catalyst there, because it's still an alcoholic compound, and then obviously the heat is a giveaway that this is an elimination type of reaction. Okay, so get the first mark by saying that the type of reaction is an elimination reaction. Okay, so remember, if we have a haloalkane and we add an alcohol with this would be potassium hydroxide or sodium hydroxide, any type of alcoholic compound at heat, then that's an elimination reaction. Okay, and then that's going to produce a alkene. Okay, so haloalkane to alkene is elimination reaction, that purple one there, and because we know molecule 3 is actually 1-chloropropane, um, as in a haloalkane on a chlorine on the first chlorine, which is our halogen on the first carbon. Sorry, so first carbon there, second carbon, third carbon, and we know that the next molecule, which will be an alkene, is going to be propene, because we're still keeping the number of carbons the same, we're just turning it into an alkene. Okay, so prop means 3, and then ene is the alkene part. Right, so that's our second mark, right? And then if you look at the alkene, we've hydrated it. So a hydration reaction, which H2SO4, H2O, it forms, what is this? This is an alcohol, because we know from the hydroxyl group OH at the end, it's all in alkanes. So this would be propanol. Okay, but we can also get a different type of alcohol. This would be a primary alcohol, because the OH hydroxyl group is on the first carbon. Well, we could have it on the second carbon, actually. So that would be propan 2-ol. So this is really, if you remember and know your diagrams, the reaction pathways, then you know that from an alkene we can get to an alcohol through an addition reaction. And does it mention addition reaction there? It doesn't mention addition reactions, but remember, with addition reactions, what we're doing is we're adding something in, right? We're just stuffing it in there. And with the H2O, that's basically a hydration addition reaction. Okay, and we have that heat, pressure, strong acid as well to counteract that. And this is a strong acid, which is H2SO4. That's a diprotic strong acid. I think that's hydrogen sulfide, I believe. Let me just search that up. No, sorry, I think it's sulfuric acid. Yes, sulfuric acid. And that's a really strong acid. And then we have H2O as well. So as a gas. So we know that um, this is definitely going to be an addition reaction. And when we're going from an alkene and going through an addition reaction, we form alcohol. And obviously we have our two types. So that's the primary and the secondary. Okay. So again, once you've drawn out these pathways a couple of times, then it's not that difficult to realize, okay, alkene can go to an alcohol through an addition reaction. What's part of an addition reaction? Well, we're adding H2O, okay, for that hydroxyl group with the OH group. And then we need a strong acid as a catalyst or a reagent for that, okay, in those conditions. All right. So our third mark is by saying that product Y will be a propan 2-ol, IUPAC name. And then we need to know the oxidizing agent for the oxidation reaction from a primary alcohol into a aldehyde. Okay. Because we know that oxidizing a primary alcohol will be an aldehyde, right? And then if we oxidize a secondary alcohol, that would be a ketone, right? But what the question's asking us to do in this case is, well, first of all, let's put the oxidizing agent, okay? And the oxidizing agent, I know in the diagram it says Cr2O7, 2 minus, but usually we add a K2 there because remember K has a positive charge, so two of those potassiums will make a +2 charge and those balance out actually. So that removes this thing right here. So typically what you'd say, and it's on the end of the sheet as well, and you can have your acid as well, H plus. But as long as the marker, I guess, sort of knows what you're talking about, like in strong acid, so that's our H plus, mild heat, have some of these reagents or oxidizing agents, then I'm sure you'll get the marks there. But I guess you can sort of see how the QCAA questions won't necessarily make you have to repeat the drawing here. It's mainly about understanding the diagram and knowing what reagents or catalysts are involved um, in between the reactions as well. Okay, such as that A2Cr2O7, that is potassium dichromate. Okay, so you could even write that down. I reckon. I'm pretty sure they would accept that. And then just remember your strong acid as well. Okay. So again, we need to talk about what molecule 1 and molecule 2 are. Okay. So the marking guide, it seems that they just basically number the molecule. So whether it's molecule 1, 2, 3, etc. in these bottom boxes. Okay, and then that would get you the 5th mark. So you need to get both of them right to get that. Okay, so remember, if we're oxidizing a primary alcohol, we get an aldehyde, so I might just write that there, just so I don't forget. And then oxidizing a secondary alcohol gives me a ketone. Okay, it makes sense because aldehyde, the double bond to O is on the first carbon or the end of the chain or start of the chain, and then ketones in the middle of the chain. Okay, so we just look at our original stimulus and we'll look at, okay, which one's a ketone or aldehyde. I know this one's definitely a ketone because we have the carbonyl group, the C double bond to O on the middle of the chain, so the second carbon here. And then we have our aldehyde Now notice we don't have an aldehyde, however, we have a carboxylic acid, okay? And remember that if we put mild heat instead of strong heat, if we put strong heat instead of mild heat here, then we can actually skip that step um, and turn it into, I believe, yeah. Uh, yeah, you can actually get from a primary alcohol to an oxidation, to a carboxylic acid, sorry, through a really strong oxidation reaction. So we can actually skip that aldehyde step. So I might take a note there as well. They don't, all right, I'll probably from primary alcohol to carboxylic acid. That's also possible as well. Okay, so keep that in mind. If there's no aldehyde, then, and you're definitely sure that it would have been an aldehyde, then we go to our next option, which would be the carboxylic acid. Okay. Um, yeah. So molecule 2 will be formed, and molecule 1 will be formed here. Okay. And just to be safe and sure, I would definitely go beyond what's on the marking sheet here and actually give the names and the types of molecules as well. So I would name this one as uh, propan 2-on, and this one as propanoic acid. And just to be really sure that I got that right as well. And I would put that right here in the box where it's being marked. Okay, so that's my fifth and final mark for that. So that's full marks there. Okay, so I hope this helped in some way. I could really only find 2 questions from 2020, basically, that were pretty good reaction pathway questions. If you have any other questions for me to go through, whether it's chemistry or any of the other subjects, please let me know in the comments. Um, Again, am aware that your chemistry is coming up soon, and your externals will be this coming week. So happy studying, and again, this OneNote will be in the description below. And good luck with everything, and see you guys in the next video.